Okay, so look at these solutions to the practice test. We've got two 12 ohm resistors in parallel. So to get the total resistance, you're supposed to use that all about using fractions. So 1 over RT is 1 over 12 for one of the resistors, 1 over 12 for the other. So you get 2/12 or a 1/6. And so if you go and flip it upside down, so if you solve for RT, it's 6 over 1, which is 6 ohms. You're going to turn both of those upside down. So we're after the answer K there. What current flows in a wire with a charge of 600 coulombs past the point in 1 minute? So what you've got there is with the current. So if you look at your formula sheet, you've got intensity of current I, a charge is quantity of charge Q, and this is a time period T. So you're going to use the I equals Q over T1. And the charge there is 600 coulombs, quantity of charge going past, and you can't put 1 in there because it's got to be in seconds, so there are 60 seconds in a minute. So 600 over 60, you're going to get 10 amps, which is going to be J. In a series circuit, the current is not split, there is not more than one path. The globes get dimmer as you add more though, yes. Okay, and you can't turn off and off separately, so that's definitely wrong, so those three there are wrong. The unit of charge is the coulomb that's in that other question. The voltage is defined as the amount of energy per charge, I'm hoping, so is that one of the ones there? Yes, L, not the others. When resistors are put in parallel with each other, their overall resistance is, in parallel it goes down because you've got more pathways there and more charges available to flow, so it should be smaller than any one resistor in the thing. When one light bulb in a parallel circuit containing several bulbs goes out, the other ones burn brighter, do they? Or do they stay the same, or do they go off? Well, they'll be the same. You should have done that in your practical. Okay. 240 volt globe, so you've got a voltage there. Potential difference is the other word to use for this. You've got a current. It's got a current of 0.2 amps, intensity of current. And you're trying to find P, the power. So there your sort of quantities trying to work with here. So you're going to do P equals DI off the formula sheet. That's the easy way of finding power. So voltage times current. So in this case it's 240 times by 0.2, which is a fifth of 240, which is 48 watts. Okay. Draw a diagram of two globes connecting in series to a battery. So battery symbol. We're doing two globes in series. So that means they're one after the other on that same pathway. And it says to add a voltmeter and an ammeter to your diagram. So we would put an ammeter somewhere on that pathway, so let's say we should put that over there somewhere, change that into an A. The voltmeter is going to measure one of the voltage of one of the globes, so we'll go just across one globe here in parallel. And obviously the plus side of here would normally go to the plus side of that, and the plus side here would also go around to that one as well. What coloured terminal of the power pack should the black terminal of the ammeter go to? Well, it should go to black thing. It should go negative to negative and positive to positive. What's the ammeter reading on this one here? So you're trying to read between 3 and 4. If you count the dashes there are 10 dashes. So we are 2 dashes back. So we want to go 0.1, 0.2 back. So that's 3.8 back from 4. Alright, two resistors are connected in parallel to a 20 volt battery as shown here. One resistor is 15, one's 25. What is the total resistance? So they're getting me to show you working out here for the total resistance in parallel. It's not series, so you don't just add them together. 1/25 plus 1/15. So we need to look for a lowest common multiple of these number that goes into 25 and 15, so 75. So 25 is going to 75 3 times, so 3 ones are 3. 15 is going to 75 5 times, so 5 ones are 5. So you're going to get 8/75 as a fraction, but you can use a calculator to work that out as well using the fractions button in between there. So you do 1 fraction button 25, plus button 1 fraction button 15, it equals, it'll give you that. You need to flip this upside down to solve for RT, so RT over 1 would give you 75 over 8. That would be around about 9.4, about 9.4 ohms. Okay. To get the total current here, you've now got the total voltage and the total resistance. You're going to use your Ohm's law there to solve that and just rearrange it. I equals V over R basically. And so it's 20 volts divided by 9.4. So you get a current of that one, about 2.1, 2.13 amps. We'll round that off. Okay, what's the total voltage and current on each resistor? If you're looking at that there, You could use the table again here, probably not necessary to because you'll have this worked out, but I'll use this as a setting out since that's where I'm going. So we've got R, V, I, just to sort of set it out. At the moment we know the total resistance is 9.4, total voltage is 20, the total current is 2.1. So we've already gone down this column here and gone across, which is the method we've been using. What you're going to decide is which of these columns is going to be the constant up and down. It is not the current because the current splits in a parallel circuit. So ignore that one here, but in this case, you'll find the voltage is the same across both of those resistors. So as a last step then, we would want to go and calculate the I here by doing I equals V over R again across this row. So 20 over 25 is 0.8 amps. Yeah. And 15 over 20, no, 20 over 15 would be 20 over 15, about 1.33, so 0.8 plus 1.3, we're going to get 2.1. So yeah, the total current there should add together to give you that one, because it's splitting up from 2.1 here, and it's going down the two paths. It's about 1.8 down that way, and 1.3 down that way. So that seems to make sense. Alright, write some rules about the voltage and currents for globes placed in a series circuit. So in a series circuit, you will find the current is constant all the way around. Is constant around the whole circuit. Because there's only one path. Whereas the voltages, when you go and check voltages across a series circuit, like this one here, you'll find that the voltages add up to be the same as that coming into the battery from the power pack. So 20 volts, you might find that 14 volts are used there and 6 volts are used there. So the sum of the voltages here should add up to the voltage that's coming out from the power pack. Okay. 3 resistors connected in series is shown to this 240 volt battery. Okay. So you 1.5 kilo ohms, 400 ohms, and 800 ohms. So series ones are a lot easier to get the total resistance. You can add them together, but make sure they're all in ohms. So 1.5 kilo ohms is 1,500 ohms. So make sure you convert that there. 400 ohms and 800 ohms. So you look at that there, you've got 12 and 15, 2,700 ohms. Okay. Total current then, you do the same thing, I equals V over R, which is, and these are totals by the way. We're going to do 240 volts divided by 2,700. Right, I'm going to do that calculator. So that's 0.089 amps. But you could write that as 8.9 by 10 to the minus 2 amps. That work out a bit better. Again, you can do voltage and current here. If you still want to stick with the table again, you've got 3 resistors here now and a total. Just sort of show this setting out again. Go like that. And go R. The I, you've got a 1,500, a 400, an 800. We've got the totals again, so we've got 2,700 ohms. We worked out the current already as well as the voltage here, so we had 240 volts, 8.9 by 10 to the minus 2 amps. And this time, that's not a very good minus 2. This time the current's going to be the same because there's only got one path here, so the current's going to flow around just through all of them the same. So you can actually fill this one up here this time. So to get the voltage here, we're going to use that last bit of Ohm's law then to sort of go through here and do V equals IR for each of those. So I'll show you working out on this somewhere when you do the test. So you can do I times IR for each of those to put those values in. So if you check these out in the calculator that I've just done, we've got 133 for that one, or just over 133, just over 33 for that, and just over 71 for those. If you add those together, you should get the total. I think we get about 237, 238 from that, but that's because of some rounding off. How does electrical resistance change when the temperature of a wire is increased? So when you increase the temperature of the wire, the atoms tend to move faster. Therefore, they're going to actually involve in more collisions with electrons. Electrons are going to have their pathways halted or because we knock backwards a lot, and therefore the resistance will go up because the current will be reduced because of those electrons getting knocked backwards and sideways. What other characteristics of a wire determines electrical resistance? You've got the length of the wire, you've got the area of cross-section of the wire, and you've got the material it's made of, the conductivity of the wire. Okay. but that one is actually going to go up as the temperature goes up because of those reasons given. Okay, 17, an 80 watt globe is connected to a 240 volt power supply. Now 80 watts means it's got a power of 80 joules per second used up. It's got a voltage supply there of 240, and they're asking for the intensity of the current. If you look in your formula sheet there, you've got a relationship between those at P equals VI. So we're going to use the version where we're trying to find I equals P over V. So we're going to go 80 over 240. So we're going to get a current of about 0.33. And again, you could write that in standard form. What is the resistance of the globe at this time? Okay, so we're now trying to find R, and we've got P, V, and I. So we've got V equals IR. Yeah. So we can rearrange this to R equals V over I, which is 240 over the one we just calculated before, 0.33. So that's over a third, so you've got times that by 3. So 240, 480, 720 ohms. Okay. Right, calculate the amount of energy involved here. So it's in a time. So you're looking for an energy and a time formula out of those we've got. And you've got power, voltage, current, and resistance. The power one's present though. So I'll be rearranging this one here. Power is energy over time, and rearranging to find the energy, power times by time. So you've got a power output from this one, 80 watts, 80 watt globe. Now it's running for 2 hours, so we can't use it in hours. You've got to get it into minutes and get it into seconds. So we need to multiply those together, and that's how many joules this will use. Just check that. Alright, so you end up with 576,000 joules, or you could do 576 kilojoules. A practical is carried out by students to determine the relationship between the thickness of a wire and its resistance. The method was as follows. So they connect the circuit as shown, making sure the voltmeter is connected in parallel to the wire shown with the position there. Turn the power back on at 2 volts and record the voltage from the voltmeter, the current from the ammeter, which will be used to calculate the resistance. Okay. Repeat for different wires and position there. Okay. So there's got some good parts to that, but is the way you can improve that. Evaluate the procedure by discussing possible problems, weaknesses or errors, and how you can improve it. Alright, so they turn the packet on just 2 volts and recording the voltage once for that then. So they could repeat an average for this particular piece of wire that's in there several times to overcome random errors when they've actually read the needle on the ammeter. They could also include the diagram, I suppose, of where this voltmeter should go so it's clear. And point out that the voltmeter should be connected positive to positive here, and which terminal they could use there is the 15 volt terminal, probably in most of our voltmeters. And again, this should be positive to positive the ammeter, negative to negative the ammeter. So they could be pointing those things out there. They should probably be specifying what sort of different wires they're going to put in there. So looking at thickness of the wire, so they should try and tell us how many different thicknesses they're going to test. They could talk about controls, making sure the wires are all the same length, maybe the same material. So there's a fair bit they can do there in terms of that. Possible errors here may be a systematic error in the needle based on the ammeter, so it could have a 0 error, or it could be calibrated incorrectly, in which case improvements would be to go and replace the actual equipment and try it again, or re-zero it. You could try a much greater range of voltages as well, because I've only said you start on 2 volts here. You could try this at a whole range of other voltages and see what you get to see if it's actually confirmed. So there's just some of the improvements you could do. That's the data they got from here. So they've got independent variable as thickness, dependent variable as resistance, and you'll be plotting that. So just make sure you do your scales for this here, that you're doing a label on the bottom here. So you've got thickness and you would have a unit for that. So make sure your units include when you do it there. Make sure your scale is simple and even. So your biggest value for thickness here is 1.3. You want to sort of spread these out so it gets to about 1.3 here. 1.4, you can just about get away with that very small scale because it goes over half the axis, but you could spread this out a bit more and go further along there. So they're going on that, and you do the same thing at the top here. You've got to go up to as high as 40, so maybe we go up in 5, 10, 15, 20, yeah, we can do that. 5, 10, 15, 20, 25, 30, 35, 40, and then you're going to plot your points, say 0.4 and 40. So 0.4 and 40 there. Yeah. 0.6 and 17.5. 0.6, 17.5, so we're around there. So you would normally draw, that's not going to be a straight line, it's definitely going to be some sort of a line of that's curved through there. Okay, so probably should be a bit lower than that, but I'll undo that and try that again. So we're going to try and sort of go through there and show a line of best fit or a curve best fit that's a bit better. Okay, so you couldn't say these two are proportional to each other, but you can say that as the thickness increases, the resistance here, which I haven't labelled yet in ohms, is going to drop. Okay, so there's your conclusion from that graph there.